before I go into this confirmation trial development, we need to quickly go through this variety of formats in which you can visualize those penalty matrices, or which can be constructed by using simple programs. You can use Excel, or you can use R and other programming languages, or you can use commercial tools which are available to generate those penalty matrices. This is again the example that we had with our chemistry. We looked at boron and zirconium just as an example. But the penalty matrices can be constructed for all factors and interactions of all factors with respect to one response. And if you've got multiple responses, it's done for the second response as well. This is the data really we need from you. The responses and factors. Now, when you discuss with factors, we probably may have to have a 5-minute chat because your data could be at different sampling rates. It's quite possible that to get one batch, you may have 8 observations of aluminium because you got 8 readings in one day. Or you may have higher sampling rate for your mold parameter process data. We can discuss that and sort of agree onto one line of observations, but then this is ultimately how the data sheet would look like. The rest is straightforward. Within sort of couple of minutes, you can upload that to a software and it gives you all the penalty matrices. You can either have your own Excel files, or you can use different R or other program data visualization packages, or you can use penalty matrix software as well. Assuming that those penalty matrices are done, we record it into a format which is then reusable. We'll go through those different sheets of creating those reports. Ultimate goal is to come up with optimal influence, positively or negatively, with process response. Optimal means that it has got larger population of 0 penalty value points, and avoid setting will have larger population of 100 penalty values. For every penalty matrix, we associate a strength value. The software associates a strength value, which helps you to rank those penalty matrices. Now, there are various ways in which you can rank those, but this particular software has got one way of ranking it. Ultimate goal is to inspect or find those penalty matrices which matter. The whole objective is to visualize this data through these penalty matrices. For this nickel-based alloy data, how to use these sheets to construct confirmation trial. And then we will use that where there is one response, which is a simple case, and then we'll use it where there are multiple responses, which is slightly complex case. And then we will go through the settings of failure mode effect analysis diagrams, and then measurable factors and measurable responses. And I'll show you some examples, and that's why we'll have brainstorming session on how do we construct a case study for your own foundry. And then we will also discuss the concept of developing a certification course and your feedback on what you would like your process engineers to be trained on and the structure, because that's what I was discussing with ICME in UK as well as different trade association on really compiling this information together and develop a new 7 Epsilon course. The first report that it generates, because once you have this penalty matrices on the back, the thing is then visualization of that data. And then you come up with a variety of factors, and as I've said, that you start with the minimum value, the maximum value for niobium, for the shrinkage defect, and then these are the threshold values which define the penalty values. And then you get number of observation as 60. If niobium is in the middle 50 range, that is your squeeze tolerance limit, then it is optimal. If the niobium is on the lower quartile, then it is bad. If the carbon is also in the lower 50%, then there is an avoid interaction. I recommend that you squeeze this niobium range. That is just an example of this summary sheets which gives you the main effects and interaction. That is how you start visualizing your data. The whole objective here is to visualize data differently. If you're using statistical packages in Six Sigma, you also visualize data but using statistical correlation. And here we put that information into Excel so that we can reuse this information. We discuss about these various quartiles. We discuss about our zirconium again. When we had this penalty matrices, we found that top 50 was optimal, bottom 50 was avoid, and then we see interaction with boron, which was optimal. It also had this avoid interaction. So what it says that the top 50 of zirconium with bottom 50 of boron is an optimal interaction, and we saw those penalty matrices as well. But the information derived from penalty matrices is again represented into different format. We also get a response so that if it is in the quartile 4, then the top 50% range is given, and it comes up with a strength value, and anything above 3 is strong, but we consider sort of 3.5 as a cutoff for main effect. And it also gives you number of interactions which have come from interaction penalty matrices. And then they're also screened and then ranked in a particular order to give you the top interaction penalty matrices. This is the legend for interpreting the strength value. The color coding, avoid if the main effect strength is greater than 3.5, optimal if the main effect strength is greater than 3.5 but it's in blue color, and if it is less, it's in italics. But it will also look at interactions and then decide whether that particular strength is shown or not. And this is the case. It is quite possible that the main effects are very weak, but when they come together, then the joint effect is strong. You have to remember how we define interactions into the penalty matrix or the bubble diagram concept. This main effect was optimal as we studied in our previous presentation. And this is the interactions report where all interactions penalty matrices are ranked. Only the important ones are shown, and then the rest are, if you recall the bubble diagram, what it showed that if the zirconium is in top 50% range, boron is in bottom 50% range, and then you see this statistics as compared to other combinations. And therefore, this is an optimal interaction with a strength value just to rank different penalty matrices. And these individual penalty matrices are weak because they are less than 3.5, therefore they were in italics. But then together, it is a strong interaction. Similarly, we can have avoid interaction. That is, if the zirconium is in bottom 50%, because top 50% is optimal, bottom 50% is avoid, cobalt is in top 50%, and then the joint interaction is bad. So you can see here that when they are together, the number of components with high penalty values are 9, and there's only one good component. So again, the data is visualized into this penalty matrix format, and then you get those interactions which are ranked. Inspecting these interactions, penalty matrices one by one, is also time consuming. And that doesn't really help you to compare variety of process report. So what we need to do is to again transfer that information into various columns in Excel which can be sorted, so that you can study impact of one level, say niobium in middle 50, across defects, or across responses, or across different files. And that data can be merged to see the effect of each factor on variety of response, or one response on variety of factors. And again, here you get lower the better, higher the better function, and then you get these thresholds which define penalty value. We've seen that in our previous presentation. You show that it is optimal, you come up with a strength, and you know the number of interactions, minimum value, maximum value, the range for that factor level. This is where you see all factors which are significant. This is our zirconium again. That top 25% is optimal. Top 50% actual strength is weak, therefore it's italics, 2.8, but there is one interaction which is strong, and that interaction was with boron. And that's where you get bird's eye view of the impact of this chemistry on one defect. And it gets then slightly complex or challenging when you have multiple responses which conflict with each other. And we will see how we can use that information to create confirmation trial. And this is what we'll do when we do a case study from your data set. We just visualize data into this format and then develop confirmation trial. The interactions is put into various columns, and the reason each data is kept into separate columns, because then you can use Excel functionality to sort or to filter different data points. So you can suppress all the weak interactions, or you can suppress or keep all the strong interactions. This is zirconium versus boron. I think because it's in italics, we can't see it clearly, but this is zirconium top 50% and its minimum, maximum, and range. Boron bottom 50% minimum, maximum range, and the strength, which was consistent with interactions penalty matrix. And once you inspect this information along with interaction penalty matrices, main effect penalty matrices, and that leads you to confirmation trial. This part is no effects report. What it says that if you've got molybdenum or chromium, if it is in this range between 15 and 15.4, it does not explain the variation in process response. And that is also very useful knowledge, which means that you can maintain the tolerance limit, or you can extend if you want to test whether there is any variation or not. So that is your no effect report, which is also very useful.